right, so now let's talk about how we can show that Mallow's CP for a full model, where the full model and reduced model have the same number of predictors P, is going to be equal to, and in the application exercise I had said P, and that was because I had parameterized that Mallow's CP. I'm going to show the slides here. I had shown this like this, where I have the residual sum of squares divided by sigma hat plus 2p minus n. And I did this because this is how your book parameterizes it, but I realized that this p here is referring to the total number of parameters in your model, which I think in this class we typically have been talking about p as the number of predictors. And so I have rewritten that to be clearer here as p plus 1, where p is the number of predictors and the plus 1 is for the intercept. So I've just rewritten that here like that, and I'm going to update the slides to make sure that we're all on the same page for that. So I've got this residual sum of squares p over sigma hat squared plus 2p plus 1 minus n. And so let's plug in what sigma hat squared is. What is our estimate for sigma hat squared? Well, in the numerator here, we still have the residual sum of squares p. And the denominator, we know that we can estimate sigma hat squared by taking the residual sum of squares and dividing by n minus p plus 1. And so that's going to be my estimate for for sigma hat squared. So I'm just plugging that estimate in. And then I'm going to pull through this plus 2 times p plus 1 minus n. Okay, so I've got my residual sum of squares divided by my residual sum of squares. And then that is divided by n minus p plus 1. All right, and so now if I kind of cancel out these different pieces, these residual sum of squares are going to cancel because we're dividing the thing by the thing itself. And then this, because it's in the denominator, but it's a division, it's going to end up in the numerator. So I end up with n minus p plus 1 plus 2 times p plus 1 minus n. All right, so this is what we've got here in this final part down here. We've got an n minus p plus 1 plus 2 times p plus 1 minus n. And so, of course, these n's cross out because we have n minus n, so that's just going to be 0. And then we've got 2p plus 1 minus p plus 1, and so that leaves us with just p plus 1. And there you have it. And so just again to mention why this is a p plus 1 instead of just a p like your book has, basically I'm saying that p is equal to the number of predictors, and I think they're parameterizing p as the number of parameters in your model. And so if p is the number of predictors, then p plus 1 is equal to the number of parameters because you always have one more parameter than predictor since you have an intercept. So that's the difference. But the math will work out exactly the same if you parameterize it the other way.